We've got what we need to do one more kind of interferometer. Take two mirrored surfaces and shoot a beam of light in there so that it bounces back and forth. This simple contraption is a Fabry Perot interferometer, sometimes called a Fabry Perot etalon. Let's analyze what happens in detail. The light that comes out is going to be related to the light that comes in, and will also be related to things like the separation of the two plates. The proper wave optics approach would be to treat it as a multiple interface situation, much as we have in the past. Setting up the three regions, writing the fields in each region, and then using boundary conditions to find the transmitted field. But in the interest of expanding our bag of tricks, let's see how to deal with the problem using more of a ray optics approach. Here's the Fabry Perot again, turned on its side, with all the multiple reflections tracked. A ray comes in from the upper left, making some angle with the normal, and we'll say it has unit amplitude. The Fabry Perot itself is two slabs of material with index N1, and a gap of width d with index N2. Every time a ray reflects going from index N1 towards N2, the field amplitude gets multiplied by a factor r. Every transmission from N1 into N2 comes with factor t. Every transmission from N2 to N1 comes with t prime, and every reflection from N2 going towards N1 comes with a factor of r prime. Do me a favor and pause the video, and sketch this thing out in your own notes, and see if you can convince yourself that all those various rays should exist and have the amplitudes indicated. This is one of those things that's just a big undifferentiated mess until you try it yourself. Moving right along, the net field reflected off of this Fabry Perot thing is the sum of all those individual rays coming off the top surface, and the net transmitted field is the sum of all those transmitted rays. Those sums aren't too hard to do, and will be convergent since each successive ray gets weaker. But wait, there's more to it. We can't treat an interference problem as being strictly ray optics. We do need to respect things like phase. And as those rays travel, they accumulate phase. After traveling some distance delta x, a ray will have picked up some phase e to the ik delta x, where k is 2 pi over lambda, lambda being the wavelength of the light in that material. So that means all those little rays should have various and sundry exponentials attached to them. Let's get started by looking at a special case. Let's suppose the gap width d is such that for our combination of theta and lambda, the round-trip phase accumulated, going from top to bottom, bottom to top, is exactly 2 pi. Then there won't be any relative phase difference between successive reflected rays and successive transmitted rays, and we can drop all consideration of the exponential phase factor. We'll take all those reflected rays and bundle them up as so. Since we've normalized the field amplitude, this is equivalent to finding the ratio of the reflected field to the incoming field. That series at the end is a geometric series, which has an easy solution. There's a t prime in here, and one of our Stokes relations lets us replace that with 1 minus r squared. We also know r is minus r prime, and so r squared equals r prime squared. So there's no net reflected wave at all, which is another way of saying that it's all transmitted, and that happens irrespective of the value of little r. Even if the boundary is extremely reflective, interference will conspire to make sure that this special wavelength, which satisfies 2d over cos theta times k equals 2m pi, will pass through the Fabry Perot like it isn't even there. Now that's kind of special, and it suggests that we're going to be able to use this thing like some kind of near-perfect filter, selecting out wavelengths according to a geometric condition. Okay, so let's go back and do the general case, where the plate separation d and angle of incidence theta could be anything. As a ray bounces in between the plates, Each round trip causes it to accumulate some additional phase, e to the ik delta x, with delta x equals 2 over sine theta. So each successive ray on either side will pick up an additional phase factor that we'll shorthand as e to the I little delta. The sum yielding the reflected field amplitude therefore becomes and we can fiddle with that, and substitute, and continue fiddling, until we get this complex ratio right here. To get something real and more interpretable, we'll find the regular reflection coefficient, big R, by doing some square magnitudes. Now some trig identities, in particular double angle formulas. That there is pure real, but could still stand to be a bit easier to interpret. Let's define something called the finesse. This is a function of little r that goes to 0 as little r goes to 0, and goes to infinity as little r approaches 1. In certain circumstances, like ours, here, now, the difference between a mirror reflectivity of 99% and one of 99.9% can be pretty significant, and the finesse makes that a little clearer. F in those cases would be 10,000 and 1 million, respectively. Also, if you define F in that fashion, it lets you rearrange big R and express it as, and that's clean enough to do some interpretation. In fact, let's go ahead and consider the transmission big T by taking 1 minus big R and graphing that. This is what T versus delta looks like for a finesse of 1, which comes from a mirror amplitude reflectivity of about 40%. As you can see, there are periodic peaks. The transmission is perfect whenever little delta is equal to a multiple of 2 pi, as we found in that special case. For other deltas, the transmissivity drops off, but never all the way to 0. In words, given some particular plate spacing and incident angle, there are going to be some wavelengths that slide right through this thing, and all others will be suppressed to varying degrees. If we punch in a finesse of 100, the peaks get much sharper. More reflective mirrors make a Fabry Perot much more discriminating. The places where the wave gets 100% transmitted are the same, but the drop-offs are much steeper. And if you plug in a finesse of 10,000, you get this guy. So this is a really sharp filter at this point. A few special wavelengths will get passed perfectly, and the rest will be cut out almost entirely. This has a whole host of industrial and research applications.